This is a video from section 4.2. We're going to look at the mean value theorem. Suppose f is continuous on the closed interval a to b and differentiable on the open interval from a to b, then there exists a c in ab such that f prime of c is equal to f of b minus f of a divided by b minus a. And this is a supplemental video, so I'm not going to prove this result. But if you were to prove this, you would have to use Rolle's theorem. Okay? Now, let's look at example 1. Suppose that f prime of x is greater than or equal to 3 and less than or equal to 5 for all x. Show that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. Now, the sheer fact that we're saying that f prime of x is bounded between 3 and 5, that's telling us that f is a differentiable function. And so, since f is differentiable for all x, we have a theorem that says f is continuous for all x. In particular, I'm looking at what we're trying to prove. And we're trying to prove that f of 8 minus f of 2 is between 18 and 30. So f is continuous on the interval, the closed interval 2 to 8, and it's differentiable on the open interval from 2 to 8. So I'm looking at those values of x inside that interval. So by the mean value theorem, there exists a c in AB such that f prime of c is f of 8 minus f of 2 divided by 8 minus 2. But we know that f prime of c is between 3 and 5, so this is given. And so I'm going to replace f prime of c with this mess up here. So 3 is less than or equal to f of 8 minus f of 2 divided by 8 minus 2, which is less than or equal to 5. But 8 minus 2 is 6. And so f of 8 minus f of 2 divided by 6 is between 3 and 5. Multiply throughout by 6, and we've proven the result. That 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. So if f is differentiable for all x, it's continuous. And then what we're doing is looking at a specific interval. And this is going to be a theme for the next two examples. Okay? Now, in example 2, suppose f is an odd function. And what it means to be odd is that f of negative x is the same as negative f of x. So f is an odd function and differentiable everywhere. Prove that for every positive integer b, there exists a c in negative b to b such that f prime of c is f of b over b. So it's one of those that looks a lot worse than it is, okay? So we got to state our given. Suppose f is an odd function, so we have this result. F of negative x is the same as negative f of x. Suppose f is differentiable everywhere. But if a function is differentiable, then we know it's continuous. That's key, okay? There's a theorem in your book that states that. Let b be a positive integer. We know that f is continuous on the closed interval negative b to b, and it's differentiable on the open interval from negative b to b. Well, the mean value theorem says there exists a c in negative b to b such that f prime of c is f of b minus f of negative b divided by b minus a negative b. So I'm going right for the mean value theorem. But remember, f is odd. And that's why we know that f of negative b is negative f of b. So this is just a little algebra now. F prime of c is f of b minus a negative f of b, add a parenthesis here, divided by b plus b. b plus b is 2b. And then f of b minus a negative f of b is 2f of b, but the 2's cancel. And you're left with f of b divided by b, and that's exactly what you want. So this was a really great application of the mean value theorem. And that's example 2. let's take a look at example 3. This is a classic problem. It's a fixed point problem. A number A is called a fixed point of a function f if f of A is the same as A. Prove that if f prime of C is not 1, that's going to be a key point. And if you don't mind, I'm going to change that to an x. So if f prime of x is not 1 for all x, then f has at most one fixed point. And so when you want to prove that something has at most 1, assume that it has 2 and show that that can't happen. So this is called a proof by contradiction. So what we're going to do is we're going to suppose f has 2 fixed points, and we're going to just call them A and B. Now, without loss of generality, I'm going to assume that A is less than B. Okay? Now, we know f is differentiable for all x, so we know f is continuous for all x. In particular, I can say that f is continuous on the closed interval A to B and differentiable on the open interval from A to B. Well, there exists a C in AB such that f prime of C is f of B minus f of A divided by B minus A. But remember, A and B are fixed points. And so f of B, this term here in the numerator, I should say, is the same as B, and f of A is the same as A, right? And remember, A is less than B. So f of B minus f of A over B minus A is B minus A over B minus A, and that's 1. And this is a contradiction because it was assumed f prime of x is not equal to 1 for all x. And so therefore, f can have at most, one fixed point. Let me change that. So let me say that again. So when we did this, we assumed f had 2 fixed points. And then we also assume A is less than B. Okay? F is differentiable for all x, so it's continuous. And in particular, f is continuous on the closed interval from A to B and differentiable on the open interval from A to B. And the mean value theorem states that there is a C in AB such that f prime of C is f of B minus f of A over B minus A. So it's a slope. And f of B is B, f of A is A, so you get B minus A over B minus A, which is 1. And that contradicts the fact that f prime of x is not 1 for all x. So you can only have at most one fixed point. And when I say at most 1, that could be 1 or that could be none. Okay? And okay, that'll conclude this video for section 4.2. It's on the mean value theorem where we did 3 examples. Thank you.